In this time, I'm going to talk about conditioned generation. In the materials, it was called Encoder-Decoder Models. You can also call it conditioned generation. And basically, so what we talked about before were language models, and language models are basically models that allow us to calculate a probability distribution. Language models are generative models of text. So if we have a sorry, if we have a sentence S, we can sample this from our distribution over language, and we can use this to generate something like this. So this was an example of a recurrent neural network LSTM language model trained on all the Harry Potter books, and then they tried to have it generate a new Harry Potter book. So the Malfoys said Hermione. Harry was watching him. He looked like Madame Maxime when she strode up the wrong staircase to visit himself. So the funny thing is, this actually made the exact mistake that I said LSTMs should be able to fix. So the subject is she, but but it's saying himself here. So interestingly, even LSTMs were not able to fix this. And then you have a bunch of other kind of crazy stuff that's generated here. So text generation is interesting, and I think a lot of people are very interested in it, but it's kind of an ill-defined problem in a way, because what do we actually want to generate? It's not entirely clear. We might want to generate a Harry Potter book, but what does a Harry Potter book look like? We have 7 examples, but we don't. 7, or is it 10 now? I don't know. But we have several examples, but we don't necessarily know what a new good Harry Potter book would look like. So a slightly better defined problem is conditioned language models, where we have some sort of specification about what we should be generating. So not just generate text, but generate it according to some specification. So we have input X and output Y. So the input X could be structured data, for example. Output Y could be a natural language description. Input X could be English, output could be Japanese. A document, a short description of the document, an utterance, a response, an image, a text describing the image, or a speech and a transcript. And all of these correspond. I picked all of these because they correspond to a common task in NLP. So does anybody know what these tasks are called? The first one's actually maybe more difficult than the others, but anybody? So this is frequently called natural language generation. In fact, this is what was considered natural language generation before we had models. So structured data. I'll give some examples of this later, but your weather reports, for example, are often generated from structured data that tells you how warm it is, how the clouds are coming in, etc. There's lots of other examples of this. This one here is translation. Next one. Summarization. Next one. Dialogue, basically, yeah, I'd call it dialogue response generation, but you can also call it dialogue itself if you want. Oh, sorry, image captioning, and then finally, speech recognition. Okay. So there we go. So you can see that like a very large number of NLP tasks are basically taking in something and generating some sort of text on the output side. And so how do we model this? This is kind of review, but I'll be happy to take any questions that people had when they were reading the materials. So the way we calculate a probability of a sentence normally in a language model is we have something that looks like this. And this is the next word. This is the context. We calculate the probability of the next word over the context and take the product of all of these. And the only difference in a conditional language model is now we're predicting Y, which is our output. And we add this additional context, which is basically our input specification of what we want to be generating. So it's this is all quite simple. And normally, you know, our go-to language model is basically an LSTM language model where we take in the previous state, the input, calculate the next state, and then use it to predict. And A conditional language model, or specifically one type of conditional language model, the encoder-decoder model that we talked about in the materials, was basically this thing here. So we have an LSTM that reads in the input in maybe Japanese, an input sequence in Japanese. And we use this to calculate a representation, and then we use this to translate or generate the output sentence. So yeah, this is our general paradigm, I guess. And were there any questions about this up to here in the materials? No? Okay. Yeah, so we also call this the encoder and this the decoder. The reason why this is called the encoder and the decoder is basically we're encoding this into a vector representation that's not the same as the text. And then we're basically using the decoder to generate something from this vector representation. The cryptography thing that I put on the extra credit quiz, actually, part of the reason why I decided to add this as one of the options is because this terminology originally comes from cryptography, where you would be encoding something into some other string, and then decoding it to generate the original string. So in this case, instead of generating a string of numbers or something or a string of like different words or something like that, here we're generating a single vector and then decoding from that vector to try to get the same thing or try to get something else, I guess. Okay. So that was all review of the reading materials. Now I'm going to talk about a detail that I don't believe I included there. When you're implementing these models, one thing you need to think about is how do we pass the information from the encoder to the decoder. So one common way to do this is if we have an encoder, the encoder can allow us to calculate a hidden state. And basically what we do is we take the hidden state of the encoder and then we initialize the decoder with this hidden state and then generate things from it. So this is a very common way. That was kind of what was in my, my diagram before. There's also other ways to do this. So another way to do this is we can add a transform between. So, for example, let's say our encoder and our decoder are of different dimensionality. We can, run this through a multi-layer perceptron or something like that, and calculate the hidden state and put it into the decoder. Then one other way is we take what we calculated from the encoder and we input it to every time step of the decoder. So basically, this looks something like this. So we have the encoder, we calculate this, and then every time we generate something from the decoder, we just re-input the representation we got from the encoder. So these are common ways of doing things. In general, most models that you use nowadays use some combination of the second one and the third one. And then the third one, when they do the third one, they use something called attention, which we'll talk about next time. So usually you both initialize, maybe using a transform of some sort, and you consider the input at every time step. Okay. So next, I will talk about ways we do generation. This is kind of a review of the materials, but I'm going to talk a little bit more in depth than was explained there. Are there any questions about this first? No. Okay. So next is methods of generation. So the generation problem, basically we have two different types of problems that we would like to solve. One is that we have a model of PYX, and how do we use it to generate a sentence? And there are basically two methods. One is sampling, where we try to generate a random sentence according to the probability distribution. And the second one is argmax. So we try to generate the sentence with the highest probability, or we might want to generate the k sentences with the highest probability or something Um, and the way we generate sentences depends on this. The common way of sampling is this ancestral sampling where we randomly generate words one by one. So this is the pseudocode for this. So basically, while we haven't reached the end of sentence symbol, we randomly generate a word according to this distribution. And one very interesting thing about this is an exact method for getting things from the probability distribution. This was mentioned very briefly in the materials, but this is worth emphasizing. So there's no better way to randomly generate samples than this ancestral sampling approach. It's unbiased and will give you exactly what you want from the distribution. That's good. Why would you want to do sampling? You can think of a number of things. Like one example that I gave was in the materials was dialogue. So let's say every time you want to give a response, you want to give a different response so the people don't get bored with talking with you, you can randomly sample instead of giving the highest probability one. Another thing, let's say you're playing a game. Let's say you're playing Go or a word game because we're in an NLP class. If you're playing a game, you won't necessarily want to do the same thing every time because then if your opponent realizes they can beat you with one strategy, they'll beat you the same way every single time. So you might want to add a little bit of randomness into the way you act or something like that. So the next one is greedy search. So greedy search, one by one, you can pick the single highest probability word. So it looks like this. And the important contrast to random sampling is that this is not exact. We can't exactly find the one best. We can if we restrict our model and do something like a model where we make an assumption, a Markov assumption, which is basically like only the previous n words have an effect. Then we can do exact search. But basically, if we're doing it in an unrestricted sequence-to-sequence model like the ones we normally use, this cannot be done exactly because there's an exponential number of hypotheses you have to consider. This leads to real problems. One of the real problems it leads to is it likes to generate easy words first. So why does this happen? If you think about it, if you know your model, if you know your model will have to generate, let's see, I am a student in Pittsburgh, or let me try to do the difficult word first. So I work as a occupational therapist in New York. So occupational therapist is a very difficult word. So your model might be bad at producing this, or it might give it a relatively low probability compared to New York, which it likes to produce a lot. And if so, it will be biased to basically output new before occupational therapist because it has a higher initial probability. So you'll get something like, I work in New York as an occupational therapist. Or something like that. So it will try to output the easier words first because they'll be given a higher probability according to the model. Another problem is it will prefer multiple common words to one rare word. So the reason why is because if you have two common words like New York versus Pittsburgh, the probability of each of these words might be, let's say it's 0.25 and 0.25. The probability of New York itself will be is 0.25 times 0.25, so it will be lower than 0.1. But because the first word is 0.25, greedy search will choose this instead, and it will basically pick new not Pittsburgh, and then it will generate New York. So the overall probability is lower, but it will basically make a suboptimal decision. So there's a couple of reasons why this greedy search could possibly make mistakes, and we need to think about better search strategies. Are there any questions about this? So there's also there's an interesting connection between sampling and greedy search. So basically, greedy search can be made equivalent to sampling if you modify the distribution that you're sampling from. So basically, if you take your probability distribution and you exponentiate it to negative infinity, or exponentiate it by infinity, and then normalize and sample from this distribution, it will become equivalent to greedy search, because the highest probability word will get all of the probability, and we'll get a probability of 1. So this is not very interesting in itself, but the kind of interesting thing here is if we replace this infinity by something like lambda, by a tunable parameter, we can sample by things that gradually approach greedy search. So you can actually kind of interpolate between these two concepts. So I wanted to point out the connection there, so you know that you can sample, and approach greedy search. It's what the model thinks have a higher probability. So it will usually be more frequent words, but it might be words that the model is more certain about. Another example would be if it's not sure about the conjugation of a verb, it might have 3 possibilities for the conjugation of a verb, and it will split its probability mass between all of them. And then it also has a noun where you don't have multiple conjugations. Then it might generate the noun first. So it's any place where it's not quite certain about what it should be doing there, I guess. Okay. So one way to fix these problems is, instead of picking one high probability word, we maintain several paths using beam search. I won't be talking about this in too much detail here, because we'll be talking about search in detail later in the class. But basically the idea is, instead of picking the 1 best, you pick 2 best, and then you expand things along these 2 best paths. So this is, if you're running into search problems, you can take a closer look at materials on this. But we'll explain it more later with code examples, etc. Okay, so we have 2 simple examples of the code for the encoder-decoder. So I will turn this over to Dan, who will explain about them. So here's the first one. Oh.
Is that big enough for everyone to see, or should I make it bigger?
Make it bigger.
Make it bigger? Okay.
Do you know how to do it?
No clue.
Oh no.
That's
Sorry.
the image.
It's over here. Yeah.
That makes more sense.
So yeah,
There we go.
there. It's a bit bigger.
Okay. Then, so the beginning of this is the same as the sentence retrieval task we did last time. We're just reading all the data. This time I'm reading in the test data as well. Make your dictionaries. So this is pretty much all the same. I guess one difference here is, well, I guess this is pretty much all the same. However, you need a maximum sentence size because when you're doing dev iterations early in training, oftentimes it won't generate an end sentence tag. So it'll basically generate forever on dev sentences until it needs to generate an end sentence tag at some point. So instead, you want to specify a max sentence size and generate up to that point if it doesn't end the sentence. Then you have your input sentence, which is split into a source and a target, and you have an LSTM, which you basically add the looked up word for each word in the sentence to encode the input, the source sentence, and that gives you this encoding. Then once you have the encoding, you can get the output from that, but you need to shift over the hidden state from the encoder to the decoder. So there's a bunch of different ways of doing this. I just did a very simple, dumb way where you initialize the target LSTM, and then you set the internal state, the S state, to be the output from the previous state, and then the tanh output of the previous state. So this isn't a particularly clever way of doing it. There's a lot of better ways of doing it, but this kind of works. Then after that, you start decoding the target sentence. And then in training, you know each word that you need to decode. So you simply add each of these as the previous ones as input. You do pick neg log softmax for the correct answer at this time to get your loss. You sum up those losses, and yeah, that's training. It's not particularly complex. Any questions? Anything you want to add?
That's good. I think we should cover generations.
Oh, okay, yeah. So for generation, you basically do the same thing up until you start decoding. Then once you start decoding, you're going to go from decode either until you hit the max sentence size or until you produce an end of sentence tag. Then instead of doing pick neg log softmax of the correct word, you take the softmax over the entire vocabulary, and in this case it's greedy decoding. So you simply choose the maximum score and you pick that as your next word, then you add it back into your LSTM and keep going. Yep. Should I do batch now or a bit later?
Why don't you do a brief overview of batching?
Okay.
So maybe just the things that change.
Okay. So this isn't particularly fast, and it helps a lot to batch it. The tricky part about batching recurrent neural network algorithms like this is you can have sentences of variable length sizes, so you have a different number of operations. There are two things we do to get around this. First, before we start training, we sort the training sentence by length, and then the source side by length, and then we batch source sentences by the length of the sentence. So this gives us batches where the source sentence is all the same size. So that's really easy to batch. The next problem is the target sentences can be a variable length that correspond to those source sentences. So to deal with that, we need to pad each sentence to be the maximum length of the target sentence in the batch. But then after you've done padding the sentences, you have a bunch of extraneous end sentence tags at the end of the sentence, and you don't want to update the model for that. So you create a mask that's a 1 if it's not a padded object, and a 0 if it is a padded object. Then once you generate the loss, you multiply the loss by the mask. So this makes the loss 0 for every element that was added in as padding. So that will no longer affect your updates, which means that your padding does not actually affect training. There's a couple of other small Dynet things to note. when you are doing lookup for batch, there's a lookup batch where you pass in the lookup parameters and then a vector of the words to look up, and that will look them up all at once. There's also a picnic log softmax batch where you pass in the expression and a vector of indices you want to pick out from the softmax, and it will do that as a batch operation. Pretty much everything else happens automatically. Questions?
Any questions about this? So we've also, in the directory, we've also included a script We've also included a script to calculate blue score, which I'm going to talk about in a little bit, and this will allow you to evaluate how well your model is doing at producing output. So let me go back to the slides. Okay. So the next thing I'm going to talk about is model ensembling. So this was covered very, very briefly in the materials, but I'm going to cover it in much more detail here. The one thing that you should know, so what ensembling does first is it combines predictions from multiple models. So if we have two models, like model number 1 on the left and model number 2 on the right, and we basically run them completely independently and then combine their predictions together in some way. So why do we do this? The basic idea behind this is that different models make uncorrelated errors. They make errors that do not correlate with each other perfectly. And in general, models tend to be more uncertain when they are about to make an error than they tend to be when they're getting it correct. So the idea is basically the model that is more certain, you can trust it, and you'll be correct more often than that will decrease your errors more often than it increases your errors. And this allows you to smooth over the idiosyncrasies of the model. These are all kind of high-level explanations. On a more low-level, ensembling is one of the things that will always increase your accuracy, and it always increases your accuracy even if your model is already really good in the first place. So this is the kind of final go-to thing that people use when they really want to be like the best number that people have reported. On the other hand, it's not really fair to compare ensembled models and non-ensembled models, so it's often common to basically say we have the best single model accuracy in comparison to somebody who went through and trained 10 models and then ensembled them all together to get that accuracy. So, that's a good thing to know when you're reporting your results. So there's different ways to combine together models, and the most common way we do it is by taking the probability vectors from the models and combining them together in some way every time we make a decision. So an example of how we would do that for a conditional language model or encoder-decoder model is that basically we would have these M models, big M models. Each model makes its own prediction. Or so, yeah, actually I have this. So this is the probability according to model M. And then here, this is the probability of using model M at this particular point. So the idea is each model makes its prediction, and you also make a prediction about whether that model is likely to be correct or not, essentially. In neural models, it's very common to set this term to the uniform distribution, 1 divided by large M. So in other words, this is completely context independent, and we always mix together the models with the same probability. One time I thought maybe it would be a good idea to not do this. So I specifically tuned the yellow thing over there to give higher weight to certain models and lower weight to other models. And the tuning process gave me something that was incredibly close to 1 divided by M. So I had 4 models, and it gave me like 0.25, 0.2499, 0.2501, or something like that. So After that, I've just been using 1 divided by m, and it seems to work for me, but there might be other cases where you have very different models where it'd be a good idea to tune this parameter more carefully, or make it context sensitive or something like that. Another alternative is very, very similar, but it's slightly different. It's called log linear interpolation. And the idea is that we take a weighted combination of the log probabilities for each model, or also called the logits of each model. So this is the interpolation coefficient for model M. This is the log probability of model M. And then we combine them together in this way. So this looks very, very similar to what I just showed you before, except the right side is a log probability, and the left side is now not a probability. It's just an interpolation coefficient, which means they don't need to add up to 1 here. The other thing is now we're putting a softmax outside here. And the reason why we need to put a softmax is because it's not necessarily the case that, that these will be well-formed log probabilities set sum to 1. So we need to renormalize and ensure that these add up to 1. The interpolation coefficient here often is also often set to the uniform distribution. And if that's the case, then we just add them together and take the average, basically. So that raises a question, linear or log linear models. So when you want to decide which one of these to use, you can think of it in logic operations. So a linear interpolation of models is like a logical OR. What I mean by this is the interpolated model will generally give a high probability to any of the choices where any of the models think it's a good idea. This is good to use with models that capture different traits or make very, or might be very good in different situations. So one example of this is, let's say you have a very high precision model that can make predictions about words. Or let's say you had a model that was based on a dictionary or something like that, that made good predictions whenever it found a word in a dictionary, but it was horrible whenever it was trying to handle a word that wasn't included in the dictionary. So this model, and then you have another model that basically is your normal neural model that makes pretty good predictions all the time, but it's not quite as good as the dictionary model when you had something in the dictionary. So if this is the case, the dictionary model might assign 0 probability to the correct words at some times. So if in this case, you would definitely have to use kind of this linear interpolation method. And then in contrast, the log linear model is it's like a logical AND. So basically this is saying the interpolated model likes choices where all of the models agree. So if all of the models say this is pretty good, you'll get a good score for that choice. And you want to use this when you want to restrict possible answers. So you don't want any answers where any of the models thinks that's a really bad idea. So that's kind of the difference between these two, and you can choose which one to use according to this. Yeah.
What do you think if we add an interpolation layer at the top of the outputs? So instead of doing like linear interpolation, you do non-linear.
So the question is, what if you add a non-linear interpolation layer on top of the outputs?
And train.
I think you definitely could do that, and you would have to train that separately. That has the advantage of possibly doing a better job than this. It has the disadvantage of having to train it separately and using appropriate data to train it. Like you might not want to use the data that you trained the original models on. You might need to use some held out data. I had a paper that we did where we basically learned these interpolation coefficients dynamically between n-gram and like regular n-gram in neural models. And that works well, but I myself have not done anything have not looked carefully at any papers that that do that sort of nonlinear interpolation, but I wouldn't be very surprised if they did exist. Does anyone know something like that? No. Okay. Well, maybe it's a good idea for for something to try. Okay. So now I'm going to talk about some other ensembling techniques that are helpful. So parameter averaging is it's kind of like an ensembling technique. It's a little bit different. One of the problems with ensembling means that we have to use large M models at test time. And using large M models is obviously slow and uses lots of memory. It will take large M times the amount of time. And in production settings in companies, this is a big barrier to actually using the model. Parameter averaging is a cheap way to get some of the good effects of ensembling. So as I mentioned, ensembling kind of smooths over the idiosyncrasies of the model. It smooths over the kind of strange things that the model does. And parameter averaging is another way to do it. So basically what we do is near the end of training, we write out models several times. So we train for an epoch, then we write out a model. We train for another epoch, then write out a model. Then we train again, write out a model. Then we average the parameters of all of those models. And this has the effect of, if any of those particular models had something strange included in them, it kind of smooths over that a little bit and tends to increase accuracy. The good thing about this is it's cheap. Sorry.
But in the previous case, every model should share the same application.
In the previous case?
I mean parameter averaging.
In the parameter, yes, they have to. They have to have exactly the same parameters. In the previous case of ensembling, that was not the case. They could be completely different.
But why is the average better than the optimal one?
The average is better than the optimal one for the same reason ensembling tends to work better than the best one. And it's just because each individual model has kind of strange points. Like one intuitive explanation for why each model has strange points is because we're doing online training. And online training tends to like the data that it's seen more recently. Like we're doing stochastic gradient descent training. And stochastic gradient descent likes the data that it's seen more recently. We're shuffling our training set every time. So every epoch, the data that each model has seen most recently is different. So that will tend to prevent this tendency to like the more recent data by basically having each of the models having seen different data more recently. So there's a number of other explanations that you come up with, but that's maybe the most direct one. Yeah. So another way of doing this is ensemble distillation. So the problem with parameter averaging is it only works for models within the same run. So basically, let's say we train a big neural model with random initialization every time. Each of these models will have hidden states, where maybe in the first model, the first hidden state is have I seen a verb in this sentence yet? The second hidden state is the next word probably going to be an animal or something like that? And all of these states have a semantics associated with them, basically. Like I showed in the previous slide, you could visualize the states, and some of them had meaning. But the problem is if you do another completely independent run where we have model 1 and model 2, the semantics for these hidden states will be completely different, right? They'll be randomly, they could be randomly permuted. And then if you average the parameters, you just get a big mess. You get a model that doesn't do anything reasonable. But we would still like to have the advantage of parameter averaging, which is that we don't have to actually run M models at test time. So ensemble distillation or knowledge distillation basically trains a model to copy the predictions of the ensemble. And what it tries to do is it tries to match the description, match the distribution. Sorry, that's a typo. Match the distribution over the predicted words. And the reason why we would want to do this is basically we want the model to kind of get the same things correct and make the same mistakes as the ensemble, and this allows for more information when we're, or to back propagate a more informative distribution than the one-hot distribution. So basically what we do is we take all the predictions of model 1, we take the predictions of model 2, and these predictions have the same semantics, right? Because we're making predictions over the same items. So if it's a language model, we're making predictions over words, and the vocabulary must be the same for both of these. And we then maybe take the average of these, 1 divided by 2, and then we use this as our target during training. This is the general idea of ensemble distillation. This paper here explains the idea of ensemble distillation very well, that it proceeds to do something completely different. So what they're actually doing in the paper is a little bit different, but the explanation is good, so I think it's a good one to take a look at. The original ensemble distillation paper is a little bit opaque. Like it's kind of hard to understand the explanation, so I think this is a better one to reference. And this, in general, tends to increase accuracy, notably even if we use a much smaller model after this distillation process. And then the final one is stacking. So the final method for ensembling, this is also useful if you have two very, very different models. But basically the idea is, if we have two different models where the prediction of output is done in a very different way, we can't do parameter averaging. Distillation might also not be a good idea because the model structures are so different. So yeah, we might have a word-by-word translation model and a character-by-character translation model. So what stacking does is it uses the output of one system in calculating the features for another. So you can basically take the predictions of one model, or maybe it's a part of speech tagger or something like that. Take the predictions for part of speech and then use those predictions as features to the input model, and then train the model to use these appropriately. Are there any questions about this?
Is it essentially reducing the covariance?
It depends on how you define covariance.
Of the two labels?
This would reduce the covariance between the labels of the different models because one is using the predictions of the other. I don't know if that's the main reason why. The main reason why is because if you have a first very different model and then you can use its inputs, basically the next model will have to predict only when the first model was wrong. So it will learn kind of to correct the predictions of the first model. And that's an easier task. That's usually an easier task than learning how to predict in the first place. I guess that's more the intuition behind stacking. Okay.
I don't
Yeah.
understand how the example works if you have like a character-based translation model and then word-by-word translation model.
Okay. So this is actually something I wrote very late at night last night, and I realized that there are much easier explanations. So I'll give you one of the much easier explanations, which is basically, let's say we have a part of speech tagger that was based on a strong feature-based CRF model or something like that. And this strong feature-based CRF model predicts noun, verb, determiner, noun. We might take an embedding from this and input this into our neural model at every time step. And then our neural model could use the fact that the CRF-based model predicted this tag and use it to basically improve its predictions. Using a character-based model for a word-based, or using a word-based model for a character-based model, maybe you could input both. One example that I was thinking of was an example where they take a phrase-based model for translation and then take the input of the phrase-based model and the source sentence and then generate a translation using a neural model. But probably something like tagging is a much easier to understand explanation of this. But actually with stacking, you can get pretty creative as long as you have two models. How you incorporate them as features is, you have a lot of flexibility, I guess. Okay. So how do we evaluate? This, I think a lot of people may have heard of it, but I should go over it briefly, which is basically, if we want to evaluate when we're generating something, we generally use a parallel test set, and then given this parallel test set, we use a system to generate translations or outputs at least, and compare these with a reference. The kind of gold standard for doing this in most generation tasks is human evaluation. So you can ask a human, is this translation adequate? Does it convey the meaning properly? Is it fluent? Is it better than the other translations? And this is often the final goal of what we want to do, because we want translations or generation results that humans like. But it's slow. It takes time for people to do this. It costs money, and it's very often inconsistent if you use something like Mechanical Turk and you aren't very careful with your quality control. So other methods to do this include BlueScore, which I think a lot of people have heard of. BlueScore, basically what you do is you compare a human-generated reference or multiple human-generated references, and you count the number of n-grams that overlap, and then output a score. And this has the advantage of being easy to use. It's good for measuring system improvement. But the problem is it often doesn't match with human evaluation. It's also bad for comparing very different systems. So this is something that's particularly important to know when you see somebody came up with some new radically different system and then said it got much better Blue scores. So one example of this is Blue tends to like very fluent sentences. It tends to give very high scores when you generate sentences that are highly fluent. And neural machine translation systems are very good at doing this generally. So if you compare a phrase-based system with a neural system and see that the Blue score is higher for the neural system, often this will mean that, or the Blue score is the same for the neural system, often this will mean that the neural system is more fluent, but it's less adequate. It's less likely to get the meaning right. So if you compare two neural systems with largely the same architecture, Blue is probably pretty good at detecting which one is better. But if you're comparing two things that are very different, it can fool you sometimes. Another one that is very widely used nowadays, it's kind of the de facto standard for image captioning, and it's also widely used in translation and stuff, is Meteor. It's like Blue in overall principle, but it has many other tricks like considering paraphrases, reordering, function word versus content words, etc. And it's generally significantly better than Blue, especially for languages where we have lots of resources like English. The cons are that it requires extra resources for new languages, and it's a bit more complicated. Another pro that I didn't write on the slide, it was made at CMU, so hey, there's a pro. Alain Levy, who was one of the inventors, is now he's at Amazon, but he comes here occasionally. Finally, one thing that I don't want to entirely discount is evaluating your models based on perplexity. So perplexity we mentioned before in language models, but I think it's actually a reasonable choice for evaluating, for example, language generation models. The advantage of it is that it naturally solves the problem of having inconsistency in references. So, sorry, actually I intended to write about the multiple reference problem, but I realized I forgot it in my slides. But basically the problem is when you generate a translation for a particular sentence, there's lots of correct translations. When you generate a response for a particular dialogue utterance, there's many, many more correct responses. And things like Blue and Meteor, they have trouble ensuring that you're not just looking at the surface differences between these multiple valid answers. Perplexity doesn't have that problem because it's basically giving a probability to all of the possible responses. So even if many are valid, if it's giving a good probability to all of the valid responses, you'll get a good perplexity. And if it's missing some of the valid responses, you'll get a worse perplexity. So in that way, it's good. The main disadvantage of it is it doesn't consider decoding or actually generating output. So if for some reason you have a big problem in your decoding process, your output generation process, then it won't consider this. But for example, one thing that I have been thinking, but not empirically validated, is this might be good for language generation or dialogue response generation things where we have lots of uncertainty in it. So we actually probably shouldn't discount this as a evaluation measure. Somebody who's working on those tasks, feel free to try it out and prove me right or wrong. I'd be happy to know the answer, but I think it's reasonable. Okay, so any questions about evaluation? No? Okay, so I'll move to the final part. This is going to be a very brief example of some things that people have conditioned on when creating conditional language models. One thing that people condition on is structured data. So as I mentioned at the very beginning, this is when you said natural language generation up until about 2 years ago, this is what most people meant. They meant you had some sort of structured data source and you tried to generate something from it. So like, for example, this is a dialogue act specification. So you have a dialogue system that says, I want to inform a user of a restaurant that has a particular price range and it has a specific type of food and it has internet. And I want you to turn this into real English or something like this. And then so you take this kind of structured representation and you generate something. Other examples are generating weather reports. So you have input of what the weather is and you output a report in text. Stock market reports. So you have an example of how the stock market has fluctuated and which stocks are increasing, which stocks are decreasing, and you generate something from that. I also found an interesting example that basically took all the census data from the US and generated textual descriptions of it. And the textual descriptions are actually very, very good. They're all based on templates. So you need to make a template, but you can generate descriptions and create a whole website that people actually want to go to just by doing this natural language generation. So there's lots of ways you can do this from structured data. This is another one. This is mine and things. So this is a shameless plug. But another thing that you can do is if you have tags and an input, you might want to generate from an input and labels. So there's a number of other examples like this. So for example, you want to generate a description of you want to generate a translation, but you want the translation to sound like it was translated by a man or a woman. Or you want it to be a polite translation or an impolite translation. So there's lots of examples of this. I have been calling it labeled sequence transduction, but there's things like this. There's also examples of labeled sequence generation where you're only conditioning on the tags. And there's things like generating a review where the review is positive about certain aspects of something or negative about certain aspects of other things. So that's another example of things you can condition. Another one, this is maybe one of the ones that captured a lot of people's imagination about this. So in 2015, there were about 4 different papers that came out simultaneously saying that we can describe images with natural language. So here you take in an image and you generate an explanation that looks a little bit like this. can now do videos as description of videos as well. I think this is really exciting in a way because, you know, if you think about it, now you can take a camera and ask it to explain a scene to, for example, somebody who's blind or something like that, and it would be able to do this with some degree of accuracy. There's other kind of creative examples that I've also cited because this is an NLP class, and I think by looking at other people's creative examples, you might be able to come up with some of your own. So one is you have a name of a recipe and ingredients, and then you want to generate the actual directions for creating that recipe. Another example is we have a description of a TED Talk. So we have the name of the person who's doing it, the person's bio, and the summary of the content. We condition on that, and then we want to generate the actual TED Talk itself. And you know, there's lots of other examples. Anything where we take something and we generate text that we can condition on are things that we can do with these models. So that's the extent of what I have today. I'm happy to take any questions. Yeah.
So I think hierarchical models are popular these days. So
Oh, okay.
you encode a document,
Uh-huh.
you encode individual sentences first,
Uh-huh.
and use those representations for
Uh-huh.
encode the document.
Yeah.
Does that work for decoding too?
Yes, it does. There's a few examples of that. That's a good question. That's something I would have, if I had thought about it, I would have included it on these slides. So that's a very good point. Maybe I'll include it something later. But basically, the idea is you have the multiple. If you're not aware of it, you have multiple resolutions of generation, where you might have one kind of very coarse resolution over sentences. And then you have a finer resolution thing where you generate words in the sentence until you get to the end of the sentence, and then maybe feedback here, etc. So this is definitely a thing that people do. The best example I can come up with at the moment is character-based neural machine translation, which is one that takes words and then generates the words character by character. But there's lots of other examples of this. Maybe we can share some on Piazza or something after the class. Any other questions? Oh, yeah.
Is there any progress on automatically generating academic papers?
On automatically generating academic papers from structured data. So, so you want to take your experimental results and generate one. No, but please tell me if you do. I think, you know, it's fairly reasonable, but if you think about how much you worry about how to write your paper, it might not be an easy problem for an LSTM to do, especially if it can't get she and himself correct. But, you know, I think one interesting application that I heard of before, I don't remember where I heard of it, so I can't come up with a reference, is taking in an academic paper and generating a structured abstract. So structured abstracts are things that we don't have in NLP, but they have in in medical or biological papers, where it's like method or question, method, results, etc. And then they take the whole paper and try to generate something like that. So I think it's interesting. It'd be cool if it worked.
So can you find that paper?
What's
Can
that?
you find that paper? I mean the title of that paper.
Oh, of generating structured abstracts.
Generating abstract.
Structured abstracts. I actually don't know the title of the paper. I can try to find it.
But I know some guy
Uh-huh.
has generated a paper and they submit it to some conference and it's accepted.
Okay, so the question or the comment was somebody tried to generate a paper and get it accepted to a conference. I think that works as long as your baseline for that conference is very low. So if they generate a paper and get it accepted to a real conference, for example, in our field, I would be very surprised. But there's also ethical concerns with doing that, right? Interestingly, so this is actually a non-trivial, or it's an important point about natural language generation also, which is why I say Perplexity is a good measure for assessing natural language generation systems. So it's very easy to generate something that looks like a real paper, right? I can download a PDF from the ACL anthology and generate a very good paper by literally taking that PDF and resubmitting it to a different conference. If you're just generating things that you've seen already, then it's super easy to generate something good because it's already there for you. You can just copy it. But the difficult thing is generating something that's both new and realistic. And the reason why Perplexity is a good measure for natural language generation systems is then you can hold out a new piece of data and see whether you give it a reasonable score or not. But if you have a rule-based natural language generation system, for example, you can't do that. So just generating something good is a very gameable metric, but measuring the perplexity of something new is not gameable, or not easily gameable. So that's why. Anything else? If not, it's a little bit early, but I'll finish up here. So thank you, everybody.